EC 111, lecture 13, Sat 6. We want to talk about signed integers now. These are used in several real-world scenarios where we don't need to do like floating point, or we don't need those additional numbers. Also, a lot of important things in life are shown by signed integers. And here we could have a if you have a sign magnitude system, that means that we have k bits for the number, and then 1 bit left for the sign. This number system has the problem that it's not easy as to do computations. It also has 2 representations for 0, and as you probably have seen this in your logic design course, instead of going into that trap, we usually use 2's complement code, which is kind of the conventional way to do this. In 2's complement system, the most positive number, again, you have 1 bit for the sign, but there is a different representation for the negative numbers. So the positive numbers are as they were before. The negative numbers are formed by finding a complement of the number. So, if you want to present say our number is 0, 1, 1, 1, 1, 1, all the way 1 to the beginning, like it is shown here. If you want to find its complement, we first find the inverse of this, which is 0, 0, 0, 0, 1 here, and then we add a 1 to it. So if imagine that this was a 7, if you represent it in 2's complement number, like only numbers to here, how you would represent it in a negative number, it would become 1, 0, 0, 1. This will become a -7. Again, here we are showing how this 2's complement numbers are getting converted into the decimal system, here you see that the most positive number is plus 127. We have one number on the on that side of more, minus 128, and this is because there is only one representation of the 0. So we have a 0 as part of the representation for the positive numbers, and then this will become 128 possibilities, and then we have minus 128 possibilities if we were talking about kind of the number of bits is 2 to the power 8 here, which is the number of bits is 8, so the number of possibilities for these is 2 to the power 8 possibilities, as you see here. Okay, so if we have signed integers, you should be able to convert between signed and unsigned interpretation. Verilog gives you the capability to do that. So if we define a number as a signed number, then you want to, because if you don't define it as a signed number, it will just treat it as an unsigned number. But this can help you do the arithmetic or the operations more carefully in Verilog. And sometimes it gets confusing. Remember, we talked about the binary numbers and how you could pack multiple bits into 1 bit to have a shorter representation. But if you do that for the last set of bits that have a 0, that have a minus or plus sign in them, it does not always translate to something readily interpretable. So it's sometimes better to avoid those kind of systems. There is also a possibility for resizing signed integer. If you want to resize something, we have seen it with unsigned integers. So if you have a number with say this many bits, and it's a positive number, then it's reasonably easy. What we do is we just add zeros here. But if you're have a negative number, then just this doesn't work. So we will be talking about it. And also, if you want to discard part of this, if you have a non-negative numbers, if you discard all the bits to the left that are 0, then you could resize your number, and you have to make sure that your sign bit is 0. And now, if there is a negative number, if you're trying to extend it to more bits, we have to extend it by ones, because this is a two's complement system. So if we have, for example, this minus 75, and we are trying to extend that further to this 12 bits, we have to have leading ones. And if you're truncating, you have to make sure when you truncate, you keep the sign bits. And if you don't want to get an error, you need to make sure that the leftmost bits to truncate a negative number are all 1. In general, for two's complement integers, so if we want to extend the number, we should extend them by replicating the sign bits, and the truncating should be done by discarding the leading bits. And if the leading bits are the same as the sign bits, then we are not losing accuracy here. In the next set, we will be talking about signed operations.